Okay, so we're going to carry on with capacitors, and we are going to do what we did for resistors all those months ago now, back in year 12 when you were doing electricity. We learned that resistors are manufactured on a massive scale, but only certain values. And then if you want a bespoke resistance, you have to start learning how to combine resistors that you have got to produce the resistance that you want. And we're going to do that with capacitors today because they are also mass produced, but only in certain values. And although it's possible to pay a very large sum of money to have a manufacturer manufacture you a bespoke capacitor, it's generally not worth it when you can just combine a couple of other capacitors, off-the-shelf capacitors, together in just the right arrangement and provide yourself with a capacitance of any value that you want. So just like we learnt formulae for combining resistances in series and parallel, we're going to learn how to combine capacitances in series and parallel. So let us start with a quick vote. Who would like to do series first and who would like to do parallel first? Bang it out on the chat and we'll go with the greatest number wins. Series or parallel? Come on, interactivity. We can do this. Ooh, series takes it. Look at that. No hesitation at all. Okay, on a piece of paper, could you draw for yourself a couple of capacitors in series? A couple of capacitors in series. Okay, we ready? Okay, so anybody want to tell us any variables that could be added to the diagram? Or any formulae that we might use? You can stick it on the chat or you can just shout it out. Anyone want to contribute anything?
Would you draw on the current?
Okay, we could draw on the current. It turns out that we're not going to need the current. So if you want to keep your notes pristine, don't add it. But yeah, it's definitely a variable that's in play. Any other variables or formulae? Sorry, that's a bit quiet. Say again.
Potential difference.
Yeah, potential difference. So we've got the PD that's going on above capacitor 1. And we've got the PD that's above capacitor 2. And we've got the total PD that would be across the single capacitor all on its own. Sorry, I know that's a bit small. That's a 2. And that's a T. Any other variables or formulae that are in play? Okay, what's the only formula you know with got capacitance in it? Type it on the chat if you want.
Q equals VC.
Very good. Where should I put this? Okay, so anybody want to give me the missing variable now?
Charge.
Yeah. So let me just move those C's for a second so I can get some Q's in as well. Right, that one's got plus and minus Q1, and that one's got plus and minus Q2. And then this one will have plus and minus QT. Okay. You might remember from resistors where we used V equals IR that we're going to use this formula to get a formula with C's in. And we're going to do that by substituting it into another formula and then eliminating something that's the same. So we're looking for a relationship between the V's or a relationship between the Q's. The way this process works is that there exists a formula for one of them, and for the other one, it's going to cancel out because they're all the same. So do you know a formula that links the V's together or links the Q's together? Or do you know a reason why all the V's will be the same or why all the Q's will be the same? Any insight into V or Q?
Well, VT will be V1 plus V2.
Very good. VT equals V1 plus V2. And that's because the rule here is that we are charging the overall capacitor up with the same potential difference that we're charging the combination up with. So this entire combination must be at VT. That's where this is coming from. The whole combination has to be at VT. Okay, which means we can do some substitutions from this formula. So we've got QT over CT equals Q1 over C1 plus Q2 over C2. So what do we know about the Q's? Stare long and hard at the top diagram and wait for the penny to drop. Examine those Q's really well on the top diagram. Maybe it'll help if I take the voltmeters back out.
Is it that the charge is the same in both capacitors?
Okay, so the charge is the same in both capacitors, but because I'm a cynical person, and I think that you could have guessed that from the fact that you know we're about to cancel these Qs, I would like an explanation, please. You've got one?
No.
Anyone got one? Stare really hard at that diagram. Okay, let me, maybe it'll help slightly if I remind you that this bit here is a dielectric, and this bit here is a dielectric. And the definition of the dielectric is that charge cannot pass through it. Does that help? Okay, let me remove more bits of the diagram. Charge cannot pass through that dielectric, so I couldn't care less what's happening the other side of it. Does that help? Okay, there are some electrons on this plate of this capacitor. This plate here has got minus Q lots of electrons on it. But this plate is electrically insulated from everything in the universe apart from this plate over here, because there's a dielectric there and there's a dielectric there. So if this plate is going to pick up some electrons, the only possible place that it could have got it from is the only other place it's attached to. And so if this place has gained electrons, this one must have lost exactly the same number of electrons, because it is only from this plate that this plate can get its electrons. You might need to be able to articulate that in a test one day, but it also, by understanding it, you get a good understanding of the flow of the charge as well. So just scribble a note to yourself as to why all of the Qs are actually the same. Well, why Q1 and Q2 are the same, and by definition, if we've got the same potential difference, we must be storing the same amount of charge. Just make a little note to yourself that Q1 has to be equal to Q2, because the negative plate of C1 got its electrons from the positive plate of C2. And in terms of Q2, well, it's got to store the same amount of charge for the same amount of potential difference. So if the top set is storing charge Q, then the bottom one all on its own has to store charge Q. Remember, they're only storing Q in total, because all we've done is move Q from one capacitor to the other capacitor. We haven't magicked up some extra charge from somewhere. Okay. We got ourselves a formula. Note that it's the other way around to resistors. So in resistors, that would be the parallel formula. But for capacitors, that's the series formula. Which means I bet you all can take a pretty good guess at what the formula is for the parallel capacitors. But I would very much like you to have a go at deriving it. So same thing as before. Could you please draw yourself a pair of capacitors in parallel? Could you label it with V's and Q's and C's? Could you write the formula Q equals CV? And then the goal is find a formula that either links the Q's together or links the V's together. Have a go. So I haven't drawn the voltmeters on mine because I ran out of space and I've only got one color pen, and it might get confusing to slap all the voltmeters on, but hopefully you've got some V1s and V2s and VTs on yours as well. So last time we added up the PDs. Is that what we're going to do this time? Are we going to write VT equals V1 plus V2 again? Is that true or false? What do you think?
False.
False. Why?
Because of Kirchhoff's first law.
Ooh, good. What Kirchhoff's first law? What does that mean?
The potential difference entering a junction is the same as it leaving the junction.
No, you get muddled up. So Kirchhoff's first law is about current, and if you just swapped all the words potential difference for current in what you just said, that would have been true for current, and that would have been Kirchhoff's first law. K2 says that in a closed loop, all the PDs add up to 0. Oh, sorry. Yeah, in a closed loop, all the PDs add up to 0. So you could do it this way if you want and say that that and that add up to 0, but which means that that one has to be equal to that one. It's just that one's positive and one's negative. But it's simpler to just remember that in a parallel arrangement, the potential difference of components in parallel are the same as each other. And so V1 will be equal to V2, which will be equal to the potential difference across the whole thing, which is just VT. So in this case, all of the V's are the same. All PDs are the same. So in this formula here, Q equals CV, eventually all the V's are going to cancel out, which is going to be great, which means we need a formula about the Q's. How do you think Q1 and Q2 relate to QT?
Does QT equal Q1 plus Q2?
It does, which again could be a guess. So can you justify it?
I don't really know.
Okay, so the rule is that we're replacing this pair of capacitors by a single capacitor, and we shouldn't be able to tell the difference, which means that if we've stored a certain amount of charge, we should still have stored the same amount of charge. So this capacitor is storing up Q1 lot of charge, and this capacitor is storing up Q2 lots of charge. And unlike last time, they're doing it independently of each other, which means that this Q1 is not the same as this Q2. It's a completely different bucket of charge, which is not the same as we just had. Let me just show you that again. When we had them in series, if we were to put some charge on that plate, it's because the Q that matches it, the negative Q, has come from this plate over here. It's still only Q lots of charge. What we've done here is just to balance out the capacitances. We've just shunted some charge from here to here, but we've neither gained nor lost that charge when we did it. We just moved some charge in the middle here. So this doesn't count as extra charge. It's only this charge that's actually been moved large scale from one place to another. So in the series example, we've only got one lot of Q's. But in the parallel example, this lot of charge up here is a completely different lot of charge to this one down here. So we really do have Q1 lots of charge up here, and separately to that, Q2 lots of charge down here. So altogether, we really have stored both lots of charge. And now it's just a case of substituting it in. So Q equals CV. And the V's cancel out, leaving us the formula that we were expecting to get. So in exactly the same way that you have memorized the resistor formula in series and parallel, I need you to memorize the capacitance formula in series and parallel, which should be straightforward to do. If you just remember, it's the other way round to resistors. And just like part of your learning was to learn how to derive those formulas for resistors, it's exactly the same for capacitors as well. You should be able to trot out those derivations with the reasoning that goes behind them as to, you know, for the series why the V's are the same, but for the parallel why the Q's are the same. Getting muddled up. For the series, why the Qs are the same, but the PDs add up. And for the parallel, why the PDs are the same, but the Qs add up. Okay. That's the learning-y bit from me. Now we're going to practice it. So there's two little things that I've got for you. Let me just share this. Oh, wrong one. So you've seen these kind of things before. This is a PhET simulation, P-H-E-T. I've put the link to it on the classroom post for today's lesson. And what you can do over here is you can select either single capacitor, and then you can have 2 in series, 3 in series, or you can do 2 in parallel, 3 in parallel, or you can go with a combination of the different types. And then you can put meters on here to show the total amount of charge and the total amount of energy. Oh no, we don't want to do energy yet. Total amount of capacitance. You can stick voltmeters on them. So for instance, here you can charge them up with some batteries, and the simulation shows you that there's the same amount of charge on both types, and it hopefully allows you to see that these electrons on this plate have come from this plate. They're not a new set of charge, it's just an existing set that's just moved to a different place. And then you can take the voltmeter and you can attach it to either side of the voltmeter, either side of the capacitor, and it'll tell you what the voltmeter is. So it's as good as you're going to get for doing an experiment while you're in lockdown. And you can just test out for yourself, are the volts the same? Do the volts add up? You know, you can do the volts there, and then you could do the volts across the top one, and then you could do the total amount of volts, and you could just check that all the numbers are working properly. You can play with the sliders for the different amount of capacitors. You can change the different potential differences. It's just a nice little simulation for making a little bit concrete through a virtual experiment, what we've just talked about, and just checking that the formula really do work. So that's the capacitor lab. You could have a little play with that if you wish to. And the other thing that I have ready and waiting for you to do, which I'm sure you can predict by now, so this is chapter 21.2 of the textbook. So it just talks you through what we have just done, using quite a lot of words, I have to say. And then at the end, there are 6 summary questions that you can be having a go at there, just to see if you understand it. Okay, so it's what, 10 to 3? You got about 25 minutes. So surely that will be enough time to have a play with the capacitor lab and answer those 6 questions. Do you have any questions?